Hi everyone, Miss Gogerty here, and we are going to dive into our next section of Unit 6 in Chapter 5. So we are just working with our integrals, and we're going to continue that in Section 3. So please make sure that you have your Section 3 note sheet ready. Today we are going to learn something called a definite integral. That's going to be our main goal, and seeing what does that have to do with the Riemann sums and the other integrals that we've studied in the previous two sections. So take a second. You can read the first three questions and you should be able to answer those relatively quickly based off of Mr. Leavenworth's videos that he's recorded for you in the past. Okay, so take a pause and then come back with me. All right, so coming back, hopefully, we're looking at what is the area under the curve between f of x and the x-axis based on each of these individual boundaries from A to B. So the first one, I can see that 12 should be my area. And whether we get back into a Riemann sum here or not, since it's given to me, I shouldn't have to do too much work to think about that. In the second area, or the second region bounded by B to C, I have a 10. Okay, so for the moment, I'm going to write down 10, but something should trigger in your mind there that something's going to be special about that 10. But just moving forward for a moment, the last area bounded by the points C to D on that interval, we are going to end up with an 8. Okay, pretty easy enough. It was given to me, but I want us to look a little bit closer at region 2. Okay, so in between the boundaries of B and C. The region is below the x-axis. So I want you to think about what Mr. Leavenworth taught you with the Riemann sums. What would be true about the area of this region and why, most importantly? So think about it. If we were to do a Riemann sum, so I'm just drawing in a left-handed Riemann sum, but you could do whatever your heart desires. If we were to find the area of each of those rectangles, what would be true? And hopefully, I'm going to come back up here and I'm going to modify my answer to number 2. Hopefully, you would be giving me a negative 10. So what's true about that region? It has an area that is equal to negative 10. So how in the world can area be negative? That shouldn't even be possible, right? Like a negative area. Well, I want us to think about, what does the negative tell you? And this is going to be important for today's lesson. The negative is telling us the direction. So as in so many of the things that we have studied in mathematics, a negative tells you direction, okay? And in this case, the direction meaning below the x-axis, okay? Now, as we continue along with that, why? Why does this happen? I mean, if we think about the area of any rectangle, we need base times height, okay? So if I'm looking at base times height, well, the base of the rectangle, if I blow this up, the base is moving horizontally. So we're reading from left to right because it said start at B, end at C. So as we move left to right, my rectangle's base is changing in a positive direction. Okay, so if I started here and I ended here, I've moved in a positive to the right. So my base on each of these is going to be a positive delta x, change in x, okay? But what about the height? Now, it's hard to say that a height can be negative, but in these cases, in this situation, the height is going down. So if the height keeps going down, well, then my height is negative. The overall height is a positive value. It's a distance, but the negative is giving me a direction. So again, here I've got a negative direction on the height. So if we consider that with our area, the overall area is going to have a negative value. Now, that doesn't mean we have a negative square footage or whatever unit I want to add on. It means that the direction is under the x-axis, okay? So keeping that in mind, it's going to be important as this lesson goes on, okay? But everything that I just talked about there should pretty much be a review. So let's expand on, what does this have to do with integration? The last section we just covered was 5.1, where you learned about an indefinite integral. And now we're looking at a definite integral. So how in the world is this different? What's going on? I want us to take question 1 And I'm just going to bring this down here that another way we could have wrote this entire question out. All those words, remember math people are lazy. We do not like to write words. That's just a little hint in case you didn't know, or a little insider tip. Well, we can write all those words with this notation. The integral from a to b of, well, I wanted area. So I want us to think about how can we represent area? Okay, well, area would be an f of x times my change in x, otherwise known as, just so you know, dx. Okay, I can swap those. Now, expand this a little bit, and I want you to think about what do we mean? A to b, this value right here is giving us our interval. So I want the area on the interval of a to b. Okay. Next, f of x. What is f of x really telling you? So if I were to calculate f of 1, f of 2, f of 3 constantly over and over again, what would that give me in this picture? So like if I knew there was a 1 here, I'm making that up. F of 1 would be a point up here. Well, guess what f of 1 would represent? A height, right? If let's just hypothetically say here's 2. Well, my next point over here, this would be f of 2. It would give me a height again. So if I come back down and I shrink this, f of x is the height of each rectangle. Okay. Delta x, let's come to here. Change in x. I've already hinted at this in this video. What is the change in x? Whoop, it's over here. If you see me circling in green, this is the base of each rectangle. So what I want you to recognize is that a definite integral, it's different from your last section, has a very specific interval given. And the way we're reading this is we're getting the area under a curve. Okay, so all this is going to do for us, this notation, going a little bit further, okay, in words, this is the sum of all the areas. Oh, sorry, I want to back that up. Sum of the areas of all the rectangles on our interval from A to B. But here's the cool part. When delta x goes to 0. Now, what in the world is that meaning? If the change in x goes to 0, what's happening if our change in x, if we're making that change in x go really, 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 really small, what's happening then? Okay, well, this is really important too. The smaller and smaller and smaller I can make this change of x, doesn't that mean the more rectangles we have? Once again, this is something Mr. Leavenworth brought up before. Every time I can make this change of x even smaller and smaller, I get infinitely many more rectangles. Imagine if I was able to make the change in x infinitesimally small. That's such a fun word. Infinitesimally small, meaning super, 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 super tiny, tinier than you can even fathom. Well, then I get more and more rectangles. I get a better approximation of the area. So overall, when we're looking at a definite integral, you are finding a way to have infinitely many rectangles underneath a curve and add up all their areas together. It's pretty darn cool. Okay, now just to throw this out there, it is not something that we are going to spend too much time on in this section, although it is mentioned if you read the section notes. Since we are talking about the sum of all the areas, this is also a summation. Okay, so like if we went back to our sequences in series that we've learned in the past, we're looking at a series because we are adding rectangle after rectangle after rectangle after rectangle. Imagine if you keep adding all these areas over and over and over again, okay? This notation can show up as a limit on our AP test. We will review this with you later on in the year. So imagine as our change goes to 0, summation means add up all the areas, okay, and think about what we're adding. We're adding up the outputs, or sorry, the height, so the outputs of every rectangle times the width of every single rectangle. So here is my height, here is my width. So I'm asking you with this symbol to add up all the areas when we make the change super, super small. And what's going to happen here is we start with a K value of 1. So like, what's your initial input, right? And we're going to go to N, however many iterations like that we want to look at. This is just an FYI that I want to put into the video so that you've seen it. And especially if you read the section, you know where that's coming from. Okay. So we just introduced the fact that Riemann sums area can be rewritten as a definite integral. Okay. Let's expand on this a little bit more and make more sense of it. Okay. This concept of a definite integral can be further explained in the application of finding displacement. Okay. So here's an application of it. So when we're given a velocity function, if v at t represents the velocity of an object as a function of time, then the area under the curve tells us how far the object is from its original position. We're going to see this. So when velocity is constant, here's something I want to highlight. The area under the curve is just velocity times time. Now, how's that possible? Now, hold on a second. Okay, so think about how we find area of a rectangle. Area is base times height. Okay, so they're saying that displacement is just going to be velocity times time, and that's the same as area? Okay, let's look at this picture. So we have a rectangle. The base of this rectangle is in terms of hours. So just for a moment, let's take hours. The height of the rectangle is in miles per hour. Okay, so if I were to multiply these together, we get out miles. Okay, well, they also told us here that velocity, just hanging out, velocity times time. I mean, it's listed for us. Sorry, I don't want that equal sign. Velocity times time is equal to displacement. Okay. Is that true? Well, velocity is miles per hour. Time is hours. Those cancels. Displacement would tell us how many miles. Hello, they're the same thing. Okay. Now, a little easier to grasp with this. The idea is already familiar. Let's look at something we understand. If a car travels away from its starting position at 75 miles per hour and travels for 2 miles. Okay, so this, by the way, should be at 75. I realize that the picture is a typo. The line was drawn at 70. Okay, so just think about knowing if I said, hey, the car's traveling 75 miles per hour, it travels for 2 hours. How far did the car go? What is its displacement? How far away is it? Well, yeah, we'd have 75 miles per hour times 2 hours, and we would get 150 miles. Okay. Well, the trickier part of this that I want you to realize is that we're saying displacement is the area of this rectangle. Well, how is that possible? Like, okay, well, here's the height of the rectangle, and that height is 75 miles per hour. That's the units given. And area is times the base. Okay, I kind of keep writing the same thing over again. The base is, okay, 2 hours. Right? Here's our base. Let me change the color. Here's my base, right? So what are we getting? 150 miles. 150 miles is the area of this rectangle. Okay. Well, here is your velocity times time, which gives us displacement. All I'm trying to convince you right now is that this notation, like displacement, can be found by finding the area underneath the curve. Okay. So the area under the curve of 75 tells us how far the car is from its starting point over a given time. Okay. So let's also take a look. I want to highlight this for you. What is this telling us? 75 dt. Okay. Well, if we're looking at it once again, here is our interval from 0 to 2 hours because we're talking about in terms of time. Okay. We're traveling 75 miles per hour. So think of it, this is right now your height. Here is your width over the interval 0 to 2, and it came out to give you 150. Okay. So once again, what this notation means is area under the curve. Okay. That is the main thing I need you to get out. Well, the first main thing I need you to get out of this video. Okay. So definite integral. It's different from an indefinite integral from our last video. Okay. All right. Let's go a little bit further because in the beginning of our warm-up, I told you it really matters that we understand what the negatives are meaning. Okay, so in the context of displacement, net signed area allows us to take direction into account. So here's another example. If a car travels straight north at a speed of 60 miles per hour for 2 hours, I know every one of you could tell me 120 miles north is where the car ended up. Okay, now if the car turns around and travels south at a speed of 40 miles per hour for 3 hours, it's going to be back to its starting position. So what's happening here? Okay, let's look again at our area under the curve. So think about it just in terms of here, this area, I have 60 miles per hour times 2 hours, which is going to give me 120 miles. So even if I took the area of this, right, and just did 60 times 2, I'm getting 120 miles. Okay. Now, on the flip side, if I take a look at just the area from down here, okay, now I got to be careful and I've got to think about those negatives, right? If I just look at it as length times width, I'm going to end up saying, hey, or base times height, my height here would be a 40 and my width is a 3. Well, okay, well, 40 times 3 is giving me 120 again. So here's 40 miles per hour times 3 hours. Okay, well, 120 miles. We've got to be careful because if we don't take into consideration the negative or the direction, you could tell me that the displacement's 240 miles, and that's not true. If a car travels north 120 miles and travels south 120 miles, then the displacement is 0. Okay. That's different from the overall, how many miles did the car travel? Okay, so we want to be careful that we make sure that our negative, our direction is coming into play. So north gave us a direction, south gave us a direction. So when we're talking about our area under the curve, we have to keep in mind that traveling north, we had we went above the x-axis, right? Traveling south, which is bringing up previous chapters, we're going below the x-axis to show direction, okay? So moving further with this, let's look at this notation that was given. So what's the area on the interval of 0 to 2? Well, the area is 120, okay? What's the area on the interval 2 to 5? That is a negative 120, and I know it's written right to the side. So our overall displacement is 0, okay? So let's kind of put this into terms of 2 different words you're going to have to be familiar with. Net area versus total area, okay? Net area refers to displacement. Okay, so overall, like we've heard this term net before. What's your net worth, right? Your net worth is like all of the positives and the negatives, like the things you own plus the things you owe money to. Then how much money does somebody have? Well, in a net area, it's what is the overall area with the positives and the negatives. So this is the sum of the areas of the regions above the x-axis. Okay. And hold on, I want to think about this. The displacement is the sum of the areas of the region above the x-axis and the regions under the x-axis. Okay. So in this case, if we say it's 120, right? And then we're adding on a negative 120 for under the x-axis, we get 0. Okay. Now, total area is a little different. This is the sum of all areas. Like, I'm going to say the absolute value of the areas, right? So if I were to ask you, how far did the car travel? Or how many miles, how many total miles did the car travel? This would be a 240. So 120 when it traveled north plus the absolute value of how far it traveled south. So I'm getting 120 plus 120. Okay. Be careful when you're answering questions if they ask you for the total area or the net area. Net area, you need to make sure you're thinking of it as displacement and including our negatives. Okay. Total area, direction isn't mattering. It's just how many miles were covered. What is the overall area of all the regions? All right. Okay. So just a few more minutes. And we want to look at our next main topic within this, properties of integrals. So if we can keep in mind that all of the notations down here mean area under the curve in between a certain region, okay? So we have a boundary, we have from A to B or B to C or whatever, then we should kind of be able to like power through this without spelling out the properties. Okay, so let's take a look at the very first one. So I'm asking you on here, what is the net area? Okay, this is important. What's the net area from A to D? That's what I want to know. So f of x is telling me the height of each rectangle. D of x is telling me the width of each rectangle. We have infinitely many of them. So if I go back to the exact same picture that I had from before, what I'm adding is each individual interval. So I have 12, then I have my negative 10, then I have my 8. So if I want to go from the boundary of A to B on that interval, sorry, A to D, then I'm going to have 12 plus negative 10 plus 8. And I could color code those, but I think you're going to be okay to say that's 10. Okay. So the next one, even easier. This is asking you, what is the net area on the interval B to C? Okay, I already asked you that. I asked you that on the very first page even. That was the second question we did. So this is a negative 10. Okay, so now let's get to the next one. What have I changed? And I want you to think about, what does this 5 do? If all of this means area, okay, what have I done to the area? All right, well, I'm hoping you can say, I've multiplied the area by 5. Even more so, another way you could look at it is we could say, here's the height of each rectangle. Here's the width. If I take every height of the rectangle, so every single one of these heights, if I multiply it by 5, isn't that going to just multiply my area overall by 5? So this is really no different than saying, hey, find the original area and multiply it by 5. So I think that's 5 times 12, which is 60. Okay. All right, let's keep on keeping on. Let's go to the next one, A to C. Okay, so I'm still asking you for net area. Every single one of these, I'm not going to keep writing net area. Every single one means find the net area. okay? Because it's a definite integral. So what am I doing by multiplying by a negative out front? Okay, I'm going from A to C, so I want this whole entire region. But what does that negative do? It's very, very, very similar to the 5 over here. Okay, in one aspect, if you want to think about it, I'm taking negative times the height. And my width, I'm just going to say that's still the same. So what happens in my picture? If I take every single height and I multiply it by a negative, we kind of have something cool happening. A rectangle that would have been going up is now going to go down. So if I had a rectangle that was going up to here and over, it's now going down and over. What we just did is we changed the direction, right? We changed the direction of each rectangle. So if I'm changing the direction of each rectangle, what would have been a positive net area is now going to be a negative. What would have been a negative net area would now be a positive. Okay, so another way I could write this is just take my area from A to C and multiply it by a negative, right? My 12 would now be a negative 12. My 10, which was negative, would now be positive. I'm getting a negative 2 as my area. Okay. All right. Let's take a look at the next one. A to A of f of x dx. So this is a little wacky. Okay. Actually, it's a lot wonky here. Okay. Let me get my coloring back on here. So I'm asking you to find the area, start at A and end at A. If you're at all doubting in your head, like, what? Okay, that means your interval is not changing. If you start at A and end at A, there might be a height. I don't know. There could very well be a height. But what's happening is there is no change in x. Okay, delta x is 0. If you start and stop at the same value, you have no width. So think about what happens when you find an area. You're multiplying the height times 0, you get out 0. It's nice and easy and to the point. Okay, last one. You should notice the slightest little change. We're going B to A. Okay, B to A, come back and explore this. That means start at B and go this way. B to A. Something is going to change in our interval. If we start at point A and go to A, start at point B and go to A, we're moving left. This lovely little change in x is going left. What is that going to do to our answer then? So my height's still the same. My height is whatever the height was before. But if my change in my width is going left, then that means this number is going to be negative. So you're finding the same overall area, but by making the change in x go left, then what's going to happen is we're going to get out a negative value. So this should give me a negative 12. Okay. So I want to look at that one a little closer. So if every change in x, so keep in mind that means that I'm doing this action. I'm making every change in x go left. So I'm going to get out a negative area, even though I see this curve being above the x-axis, okay? Because it wasn't the height that got changed to negative. It was the width of each rectangle got changed to a negative, okay? We just saw something in the example over here that also changed a positive area to a negative area, okay? All because we multiplied by a negative inside. What this is telling me is that if I looked at an interval like this, okay, if this gave an overall negative, or oh, I guess I don't want to call it negative. I want to refine that. I'm so sorry. Okay. If this changed the direction of each rectangle, okay, I want you to just realize there's another way we could write it to change the direction of the rectangles, okay? Meaning, what if I wanted you to go from A to B? So start at A, go to B. What else would you need to do to make the overall area go negative as a, meaning under the curve? Could you see it as a negative out in front? Okay. So in this example, it's the dx, the width, that's negative and changed the area. In this example, by multiplying by a negative, you're taking the area under the curve and you're flipping its direction. Both of these are equivalent. Okay. All right. So we just saw examples of the properties and we're putting them in the terms of our Riemann sums from Mr. Leavenworth. So here is a straight up list of the properties. And hopefully after what we just talked about with numbers, this makes a little bit more sense. Okay, order of integration. We just talked about this one. Okay, literally just ended with it. So what is this doing? In every single one, no matter which way you write this, we are switching the direction of the rectangles. I'm sorry, my writing's a little bit sloppy there, okay? Whether our change in x is going from left to right, or if we're just multiplying by a negative overall. Okay, the next one, equals 0. Well, why? Like, why does it equal 0? There's no change in width. Okay. All right, the next one. If I'm looking at this, what happened when we multiplied by a k? The example we saw here was multiplied by a 5. Okay, so if I multiply by a 5, we were able to pull the 5 out in the front. Well, why? Because we're just multiplying the height of the rectangle. You're just multiplying the overall area by a constant. Okay. And what happens if we multiply by a negative? Okay, well, here it is again. If we multiply by a negative, well, you're switching the direction of the area, right? Like you're switching the direction of the rectangles. So what was above the x-axis went below. What was below the x-axis went above. So I'm going to just say again, we're switching the direction. Switch, how about I spell that right? Switch the direction of the rectangles. Okay. Next one, sum and difference. This just means that we're adding the different regions together. So think of this as the net area. So I'm going to combine the areas, and same with the additivity. So both of these, I'm kind of looking at it the same way. You are combining our areas, combining each region. Okay, combine area of each region. And then lastly, the constant, we didn't just see this example, but it was earlier. So this is like the first page, like a car is traveling 75 miles per hour. So just 75, there's no 75x, anything like that. Okay, so what's happening here is that imagine if this had just been a to b of 75 dx. Well, this gave us a picture, whatever a is to b, we're traveling 75 miles per hour. Here's what's happening. So this is what we saw in the previous examples. So think about how you would get your area under here. Wouldn't you just take 75 and multiply it by whatever b minus a was? Okay, this is giving you a perfect rectangle. And I should say one perfect rectangle. Okay, so that should make some sense to us. All right, so let's quickly finish this off. And we're just going to look at a few of these that now, all right, if I give you a graph of y equals f of x, and you even have nice little squares here, can you read each of these definite integrals and understand what it's asking you to find? So in number 1, if I look at on the interval of 0 to 2, so what they want us to do is say, what is this area, okay, of f of x dx? So I'm looking at this as I've got, I could count the squares, or I could just break out some geometry, right? Like here's a nice little triangle, yay. So here's 2, here's 2. So this area is 1/2 base times height. Nice area formula for a triangle. So that gives me overall a 2. And then 2, and then I've got 1 and 1. So I'm getting 4. The area between 0 and 2 is 4. Okay. Now I'm going to clean that up because I am going to bet that I'm going to need that later on. So this whole region in orange is 4. Okay. Now let's go on from 2 to 5. Okay, so this is asking you what's the area from 2 to 5. This question was asking you what's the area from 0 to 2. Okay, 2 to 5. I've got a different shape now. I can't just count it up. Maybe I can, but I want you to look at this of what picture does this look like I have? Okay, so if I'm looking at this lovely picture, it kind of to me looks like I've got some sort of a circle. So area of a circle is pi r squared. I don't have a full circle. I only have a fourth of it. So 1/4 pi r squared. And the radius is 1, 2, 3. So if my radius is 3, I've got 1/4 pi times 3 squared. So I'm thinking that's 9/4 pi. So 9/4 pi is my area in here. Okay. Next one. So I want the area from 0 to 5. Okay, well that's easy. 4 plus 9/4 pi. Take the area from 0 to 2, add that to the area from 2 to 5, and we're in business. Okay, next one, the area from 5 to 9. Okay, so the area from 5 to 9, again, I'm seeing this as some sort of circle, right? That nice little curve sure looks like a circle. So I've already talked about how to find the area of that. So let's just do it. The radius looks like 4. So I'm going to have 1/4 pi times 16, otherwise known as 4 pi. Okay. All right. So we're almost there. Number 5. This is one of our properties. I just haven't needed to use it like too much because, ooh. Catch me on number 4. I did something wrong before we keep going. It's below the curve. That would have been bad. So number 4 needs a negative 4 pi because we want to definitely show the direction that it was under the curve. Okay, so number 15, looks like I've got one more region that I need to find the area for. And this is a nice little right triangle. So I could take the time to count it up, or why not just very quickly 1/2. The base looks like 1, 2, 3, 4, 5, 6. Height looks like 1, 2, 3, 4. If you want to call it a negative 4, you go right ahead. But overall, I'm getting a negative 12 because it is under the curve. So if I wanted my overall area for number 5, I'm going to have a 4 plus 9/4 pi plus negative 4 pi plus a negative 12. So when it's all said and done, I think pretty easily, I'm not going to spend too much time on it. I'm pretty comfortable there. Okay, 6, nice and easy. What's the area from 4 to 4? There's no change in x. There's no rectangle I could possibly draw there. That area is 0. Okay, next, 7. What is the area if we start at 5 and go back to 0? Okay, so now notice I've changed the direction. If we were doing a Riemann sum, which we are, we're doing infinite of them, we would have a change in x that's negative. So whatever my answer was from number 3, I'm just reversing it. So negative 4 plus 9/4 pi. Okay. Just as an acknowledgement of using the property, we could change the direction pretty easily if you would like to see it written that way. Okay. Number 8, same thing. I'm noticing it's going from 9 to 5. So 9 to 5 means I'm taking this and going backwards. So we are switching the direction. 9 to 5 should be the same thing as negative 5 to 9. So 4 pi should be my answer. And then we're almost there. 0 to 2, number 9, a 5 times f of x dx. All right, we are multiplying the area on the interval of 0 to 2 by 5. Okay, well, we already found the area of 0 to 2. It's 4. So I have 5 times 4. My answer is 20. And lastly, this one might be a little bit different, a little bit tricky. So what am I asking you to do here? Well, imagine if I took my function f of x that was up here. I don't want to do this, but imagine I shifted it up 3. Okay, that's what this plus 3 is ultimately doing. Well, by our properties, what we can see or what we know is that we can separate this. Like, let me know what is, sorry, I forgot to put my dx in there. Let me make some room. We can take the area of each individual piece. So, okay, let's look a little closer. I don't like 2 to 0. I'm going to switch this around and say 0 to 2. This switched my direction. Okay, plus a negative. I'm switching the direction. Okay, so this one was pretty straightforward. I can find negative 4. But let's think about what this one means. Okay, we have from 0 to 2. So here's 0, here's 2. We have a line coming straight across at 3. I want to know what is the area of this region. I'm hoping it's okay to say 6. Negative 10. Okay, there is my overall area. So ladies and gentlemen, we will for sure continue this in class, but hopefully this gave you a good understanding and solid explanation of a definite integral. All right, have a great day, everyone.